video. We are going to do something that would fall under energy balances, but not reactions or anything like that, because that's not what Dr.Berk does. So this question here is the favorite type of question that Berk enjoys. It's a type of question that you give to him on his birthday, and he'd probably give you a bonus mark. I mean, that's how much he loves these. And that type of question is countercurrent systems. All right. And yeah, Berk just seems to enjoy them. So chances are, if you never had them on your midterms or quiz, that probably means it's on the final. That's what's the case in my year. Now, countercurrent systems are quite interesting. They're all over the world. Examples of them would be like fish when they breathe. That's all a countercurrent system. But we also use them for chemical engineering as a way to possibly heat substances and everything. Now, the question I've chosen, it's going to be in the description of the video. There's going to be a photo link. If not, you have your textbook, your new one. It should be question 8.31. Now, there's also question 8.32 is also countercurrent system. That one I'm not doing, so I encourage you to do that one after you've properly understood the material. Now, this question here takes takes a decent bit of theory just to start off. Okay. Now, the first question that we have, okay, it says that we have a propane going to the system, and it's going to exchange heat with water. That's what it's essentially saying. Now, the very first step, okay, is going to simply draw out our diagram. Okay, so please take a couple seconds and try and do that on your own, and pause the video if you have to. So, if you've drawn it properly, you should get the following diagram. Now, this is the final answer for question A. So what is going on here? Okay, what's going on here is that if you got your 100 moles of propane, it's at a low temperature of 40 degrees, and it's coming into this heat exchanger that would be in there, and it's meeting up with this water that's coming in. It's at water in the vapor state of matter. It's very high temperature at 5 bar, and they're going in there, and there's the heat exchange membrane allows for the thermal conductivity to pass on heat, and as we know, heat always travels to the direction that is colder. Okay, that's the laws of thermodynamics. And once they've done their exchanging, they simply exit at their own respective sides, and we see that water is going to be in the liquid state of matter. It's going to be saturated. We don't have a temperature there. Will that be an issue? I'll tell you later. We'll find out. And then we see here that our propane, now it's nice and hot, so we can use that for whatever purpose that we want. Maybe it's going to be for combustion later on in a factory or something like that. And yeah, so that's exactly what a heat exchange is. Okay, it's transferring of heat, transferring of energy, and it's our job to now find out how much energy has transferred, how much water we need in order to heat up this amount of propane. At these pressures and at these specific temperatures. Okay, and so that's question A. Now for question B, B says that it wants us to calculate the values of the specific enthalpies in the following inlet and outlet enthalpy table for this process. Okay, so they're giving us that thing. So let's start and get to it. Now, we're going to have to use in this case I'm only using one textbook. I'm simply using your chemical engineering principles, the latest edition, and you're going to be using tables B2 and B3. Okay, that's where you'll find information for the water, as well as the propane values for the CP equation. Okay, so when you've gotten all that shown, okay, when you've gotten all your information written down, this is what it should look like. Okay, for the water, it's the most simplest. All it says is that with those reference temperatures and pressures, the water should be coming in with an enthalpy of 3065 kilojoules per kilogram. And the water, saturated liquid, but we didn't have a temperature for that, it should give you 2747.5 kilojoules per kilogram. Now the reason I'm saying, we don't have a temperature for that is that it doesn't matter when it's a saturated liquid or if it's a saturated vapor. Just whenever you use these charts, it's giving you 2 degrees of freedom, and in order to use them, you need 2 degrees of freedom. So either you say temperature pressure as your 2 degrees of freedom, or you say something like, here's a pressure with this, and it's in a state of saturated vapor or saturated liquid. That's the extra degree of freedom that you're missing. So with that, you're able to find the enthalpies coming in out of the water. So that was really easy, the water. Unfortunately for propane, you got to do a bit of math. If it was just looking at the chart and in chemical engineering, life would be so much easier, but that's not the case. So in these countercurrent systems, we do a little trick, a little mathematic. We change what the base temperature, the reference temperature is, to make our life easier, because we don't want to start doing more math than we have to. So for propane, the enthalpy coming in is 0, because we assume that everything in the system is operating, it's at reference at 40 degrees Celsius. So we don't have to do any, we don't got to find the enthalpy coming in. Now, for enthalpy coming out, we got to calculate what it would be at the difference, the difference between the enthalpy at 240 and at 40 degrees. So in order to do that, you use this equation here. Right now I have the math set up already for you, but the equation is that energy is equal to the change in temperature times the specific heat capacity on your temperature interval. Okay, so this is the base equation. Now after that, you would just simply, in your textbook, you have all those constants A, B, C, D. You simply take them and you plug them into the equation. So here, for example, 68.032 times 10 to the negative 3, that is my A constant. Keep in mind, like here, this is before I integrate, while here in the black writing, this is my after integration, okay? Make sure when you integrate that you always divide it, do your proper cal 2, and you divide by 2, divide by 3, for the power rule. Now, 22.59 would be my times 10 to the negative 5 is my B constant, and C is my negative 13.11. That's the C constant, while 31.71 times 10 to the negative 12 is the D constant. Some of you might be wondering, what the heck is this times 10 to the negative 3, 10 to the negative 5, negative 8, negative 12? If you look at the top of your chart, it will say, like, the numbers they show is before it's being scaled down. It's just, that's the way the chart is. They don't have enough space to put anything, so they do times like 10 to the whatever up at the above. You'll see it with respective column. Okay, so what you would do now, you would integrate this, so you get this 68.032 times 10 to the negative 3 times T. So what you do is you'll plug it in with 240 first time, and then you'll plug it in with the 40 degrees Celsius. And then you do it for each temperature, and you should get these two numbers for the entire for the entirety. And what you'll do is you do 22.25 minus 2.899, and you do the difference, and you should get 19.36 kilojoules a mole for the change in enthalpy of propane. Okay, and that pretty much finishes up your part B. Yeah, it can be a bit tricky, honestly, punching all these numbers, but just sometimes double check, should be okay. Yeah. Now for question C. So what does this 19.36 kilojoules per mole mean? 19.36 kilojoules per mole means that for that amount of propane and that temperature interval at that pressure, that's how much energy you need from the water to heat it, okay? So the water's change in enthalpy is super easy. It was simply taking those two reference numbers, H out minus H in, and if you do that, you'll do 2747.5 minus 3065 kilojoules, which gives you negative 318 kilojoules per kilogram. That's your change in enthalpy for water. So the question specifically wanted a 100 mole basis. So that's why we're going to say, okay, so for 100 moles of propane, how much kilograms of water do I need? Well, 100 moles of propane needs 1,936 kilojoules to heat it up. And that's how much kilojoules we need. And we know that the water per kilogram basis can give us this much energy, 318 kilojoules. So your desired amount divided by how much a kilogram of water can provide, and that gives you the amount of kilograms of water you want. It's very easy. You can just see the units right away. So the question wants a volumetric ratio between the two, right? So you might just say to yourself, oh, just multiply it. 1 kilogram is what? Is that 1 liter of water, right? Yeah, that's easy, right? No. Keep in mind that's a standard temperature pressure, so you actually have to go into your book, I believe it's B3 in this case for the water, and check what is the density of water at 5 bar. So you do that and you'll see it's 0.522 meters cubed per kilogram, okay? And these are with the specific characteristics that we have. Now, for the propane, we want to find that volumetric amount as well on a molar basis. So we just simply use our good old Pivnert, and we say, okay, well, V is equal to RT over P, where T is in Kelvin, and we say, okay, 8.314 times 313 Kelvin divided by 250 kPa, and we have to divide by 1,000 here, because remember, we want meters cubed, and normally the 8.314, I know I didn't show the units, but this setup here is for liters, and liters is 1 decimeter cubed, and the difference between a meter cubed and decimeter cubed is a factor of 1,000. So we divide here by 1,000, giving us 0.0104 meters cubed per mole of propane. Now, we have our volumetric amounts. Now we want to find the actual final answer. So the final answer here, okay, so we know that it takes 6.09 kilograms of H2O to heat up 100 moles of C3H8. Now, this is important because the question originally stated it in 100 mole basis, but that kind of messes you up for the final answer. So you've got to sort of unconvert it if you get rid of that factor. So we know at 1 kilogram of H2O is 0.522 meters cubed. So you simply do the multiplication, and you'll get that for 1 mole, 0.03179 meters cubed of steam is required per mole of C3H8. Now we want the ratios. So that's the amount. This is the ratio before being reduced. So you simply divide it by that the other number we found for the propane, which is 0.01041 meters cubed of propane per mole of propane. So it looks kind of nasty here, but the moles will cancel out. This disappears, and you're simply left with a nice meter cubed to meter cubed ratio. And that will give you 3.06 meters cubed of steam per meters cubed of C3H8. Now the last question, it kind of sounds a bit complicated, but it's actually easier than everything you've done up till now. So the question says, calculate the heat transferred from the water to the propane. That could sound quite a bit of work. This could be, depending on the question. But they say, just either do it from the water side or do it from the propane side. And I did both for you here. It's very simple. So what is the energy transferred? Well, energy is equal to, for specifically as an example, the mass of water times its total change in enthalpy, okay? So that mass of water we said was 6.09 kilograms per 100 mole basis. And we know that we had calculated it was negative 318 kilojoules per kilogram. That was the change in enthalpy for the water. So simply multiply the two, you'll get negative 1936 kilojoules. Or if you do it from the propane side, okay, they're always going to be different signs because one is giving energy, one is getting rid of energy. One is receiving, one is giving. And you'll see it's again 100 times 19.36 kilojoules per mole gives you the exact same answer, just a different sign. This is for the propane, okay? That's all it is. And the last question is just, it's just pure theory. Over a period of time, what would happen if the heat exchange membrane would become dirty and it would become less efficient? Well, what's the purpose of our experiment? It was simply we wanted to see it increase the temperature of propane. So if it's not less good at heating it, so the propane, that means the propane is going to be cooler, and that means the water is going to be hotter because it's not going to give as much temperature as we would like it to. Okay, that's all it is. So that pretty much sums up the countercurrent system. Again, this is Berk's preferable questions that he likes. It's, it can take a bit of getting used to looking up these charts, doing these integrals. After a while, it just becomes habit. Other things he could throw at you. He might, throw in a throw in the cost of this. So he might say, well, if 100 kilojoules of energy costs the plant $10, how much would this cost for this operation per mole or something, or per 100 mole basis? Well, you'd simply take your 1936 kilojoules, you'll multiply it by $10, and there you go. You got your how much it would cost you for this at these specific temperatures and these specific amounts. He might also throw in, okay, well, how they say was that heat exchange membrane was getting dirty. Well, maybe he'll give you a specific number, like it's the efficiency of the exchange is only 75% efficient now. That special thing that looks like an N, that's the Greek symbol there. So then you'll say, okay, so that means you do the inverse of 0.75. That's 1.333. So that means you'll have to make your things work 1.33 times harder in order to get the same desired temperatures to make up for that poor conductivity of only 75%. Okay, so you just multiply all your math by a new factor multiplication. It's not the end of the world. If you can do this part already, you can also do those extra bits. That's what you should expect come the final and everything. Still, this was definitely not one of the tougher questions. And yeah, that's pretty much it. So you should feel comfortable with this, looking up the charts and everything, doing the integrals. Hopefully now maybe this is your favorite question too. You'll have something in common with Dr. Berk. Hey, that's great. But apart from that, guys, thanks for listening. Hope you learned something, and thank you. Bye.